continuity or conservation of mass. Most of them are just the same, right, correctly. And the force is obviously integral force. Integral, it's not differential. Now, the second one is the same equation, continuity, right? The same, but differential. This equation, what type of equation is it?
That's the differential form of momentum.
A momentum, but what momentum?
In the x direction.
X momentum, that's an X momentum. Don't worry, if you write momentum, I accept it. Okay. You see, the idea is I'm trying to make a name quiz, but a little bit more advanced. So later, if people see our class like ABEP review, those people are coming and randomly pick some of the either quiz or midterms and say, what did you give a student to solve? And if it's more name quizzes, then it's something is like suspicious, right? So we try to make it like more legit. So X momentum and differential form, I just write diff. And then the last one is what? Conservation of energy, or simply energy equation. And integral differential? Integral. So that's the answer to that. Now let's go back to the class. And we want to do a few problems today. So the first problem, we already started this differential forms, and today we are going to use differential forms to find the velocity profile. You see, it's called velocity profile, and as you can see, it has a pattern. It's not always constant. The inlet, we can assume it's almost constant, right? But because of the existence of viscous walls, the flow gets a little bit, you see, viscosity here, so you get attenuated, and then finally you reach to a pattern that is almost like parabolic. So this region, what they do, because this is a very frequent problem, it happens in a lot of different fields. Not only it happens in piping engineering, but also it happens in aerospace, it happens in marine, everywhere. So it's some sort of pipe, not exactly constant cross-section like that. It may have a geometry like intake of the aircraft engine, right? It's just like that. So initially, you have an invasive flow, but the moment it comes and attaches this wall, initially this diffusion of momentum from the walls, because the velocity of the wall is zero, right? Propagate and you get it converts to a parabolic. So the point is, after this point and so on to infinity, the same pattern exists. You see, only from the inlet to some distance, like let's say L effective zone, you have a very weird pattern that is not repeated. Right? But after that, L effective, this pattern is going to be same. Right? So you have the same pattern going to infinity. So this is a typical of a pipe flow with an inlet, and we want to use this type of equation, the differential form, to find the velocity profile. I know that from the physics, if I go in the lab, if I create a setup, if I put a pivot here to find the velocity, I can measure velocity here, zero, go up, the velocity increases, and then you go up, velocity increases, and then you go back to zero. Just like we did with the propeller experiment. Those who had propeller experiment last week, they had this sensor to measure the velocity, and they could see a velocity profile. We can do exactly with a pipe flow. But look, if I don't do that in the experiment and I start with the equations, right, with zero assumption, can I get the parabolic profile? Like that profile you see at the end? No. Maybe yes or maybe no. We'll see. That's what we're going to do today. And it's very, very surprising, and it's very like a human achievement. that you start from the basic principles and you come up with a velocity profile. It's just amazing. The first person who did that, it was just so surprised. Alright, so you kind of predict the nature with just a bunch of equations. So that's what we're going to do today. So next slide. One thing before I go to the next slide, if you put a pressure gauge after this point and so on, just like we did the bench flow in the lab, we have this pressure gauge. After this point to the infinity, the pressure will drop constantly. That means dP dx, if this is my x-axis, dP dx is a constant value and is a negative number. Right? It's a constant value and it's a negative because pressure is dropping. So the slope is constant and negative. Now, the next slide is basically, this is what you see after the end, the dimension, it goes to infinity. So that's one of those areas, and we have some velocity profile, and it's repeating, right? It's just repeating the same thing, and the velocity, the pressure drop, dP dx is just a constant negative number. Now, I want to start from scratch the equation, the differential equations, and come up with a solution for that, hopefully. And they call this the Poiseuille law. We had it last class, so it is more extensive form of that. So let me start with the differential equation. So we have the first one, partial rho, partial t plus rho u x rho v y rho w z plus 0. This is the 3D compressible continuity equation. This is general continuity. Now, this equation number 1, call it, equation number 2, x momentum, so we have partial, let's write it in the rho separated, so you have rho, partial t, plus rho u, partial u, x, plus rho v, partial u, partial y, plus rho angle partial u, partial z, is equal to negative pressure gradient in the x, plus rho g in the x, if you have any, plus mu, the second derivative of u in x, second derivative of u in the y, second derivative of u in the z. So that's your x momentum, the general compressible x momentum, and you also have the effect of gravity, which most of the time is 0. Now, equation number 3, this is your y momentum, rho v dt plus rho u partial v partial x plus rho v partial v partial y plus rho w partial v partial z is equal to negative pressure gradient in the y plus rho g in the y plus mu partial v square plus second derivative of v, second derivative of v, equation number 4 is the z momentum. So you see, if this is my xy, if I make it a two-dimensional flow, imagine we make this two-dimensional flow. So this is your x and this is your y, right? Then, in fact, there is no z. You see that? Let's say this is not a pipe. This is just two plane. In fact, this part is maybe a little bit misleading. Consider this is true plane that the flow is diffuse. There you go. So in fact, the flow is developed between these two. You see that? Like this. There you go. It's very, very similar to the part. In fact, the equation called the shape of the equation is same, but because part is circular, then you have a little bit difference. But look, we're talking about two planes, the up and bottom. For that, if I put my x just like that, if I put my x here, you see that's my x. And then I put my, instead of r, I put my y here. You see that? So do I have the z component? So this is your z. X, y, z. Do I have z component?
No.
Velocity u is what direction? Only x. You see that? In fact, let's put this x, y, z, let's put it at the center. So I'm going to put that, use a different color. I'm going to put this here. Right? I'm going to put it just in the center of that. Three bags, four bags. Let's put it in the center of this. So that's your x. And then this is your y. And then your z is this way. Now, you see that I do not have the u velocity, this is u. It's a function of y only. Do you see that? If your y is negative value, you get something. If your y is positive value, you get something. So it's a function of u, it's a function of y. And it's not a function of z. That means you don't have v. V is 0 and w is also 0. No velocity in this direction. You see the velocity only in this direction, and no velocity in this direction. So keep that in mind when you want to simplify this relation, use that figure to decide which one is which. Now partial, let me write this. Even though I don't have W, I'm going to write the equation and then we go over it and say it's 0. Plus rho u derivative of Wx, rho v derivative of Wy, plus rho w z negative p z plus rho gz plus mu second derivative this with respect to x, with respect to y, with respect to z. And finally, the energy equation, which I'm not going to write it, but you can also work for energy equation and find like temperature distribution across the, but we're not interested in the temperature distribution. We assume that the temperature everywhere is same. But if you have high speed flow, like in the aircraft engine, then you need to also expand the energy behavior and solve for that. So let's start with this equation. And for this equation, I want to go over every single term. For example, with this, I assume that my flow is, let me change this slide. Because we want to use the one on the right. So here, I assume the flow is not changing with time. You see that? So I have the same pattern like this to infinity, and it's not changing with time. It's time independent. So what can I say about this particular term here? ddt. All ddt's are what?
0.
All ddt's are 0. It's steady state. Call it steady state. Right? Now, also make assumption incompressible. Incompressible. So with incompressible assumption, Well, in fact, the flow that we use, for example, the one that we're using downstairs in the lab, is water, right? And it's very small, so it's incompressible. For incompressible, you can take this flow out, right? You can take this flow here, put this flow here, and put this flow here. The rest are in good shape, right? So you can take this row out because the row is not a function of XYZ location. It's not going to be different. It's same all over the flow. Now, what other term is zero? Let's start with this. What do I get for that? Partial V, partial Y. Do I even have V? You see? The velocity is only in the X. Right? Do I have a V component? Forget this profile?
No.
Do I have a V component like here? No. So this term is everything is V is zero. So not only V is zero, but also its derivative is zero. If the function is zero, if you take derivative with respect to x, y, z or anything, is zero. So this term is what? Zero. What about W? Do I have the W, like the velocity in this direction? No, no. I only have U. So this term is also zero. Right? What about this term? Is this zero? What is U? Let me draw it here. That's your velocity profile. Look at the top right. So that's your U. And this is your X. And this is your Y. So this is Y0. So U is U of Y. So the derivative of U with respect to Y, is this zero always?
No.
No. This is a number, right? But look, this multiplied by V. V is what?
Zero.
Zero. V times that, whatever it is zero. So this entire thing is zero. Right? What about this? Zero. Because W is zero. What about this? This is, in the next slide, let me bring it. We have this derivative is a constant value. So this is not zero, this is what? Call it alpha. So negative P over X is alpha, equal to alpha. That's exactly what I see. Instead of the constant, call it just alpha, right? What about rho gx? Well, what is G? G is the gravitational field. Now, if the part is just a small part, like this diameter or this diameter or this diameter, the gravitational force is very small compared to the pressure force, right? G is not always zero, but in this case, it's zero. So we can say compared to the pressure force, this is just negligible. So you can say it's zero, it's zero. Everywhere you have G zero. The gravity is not the driving force. The driving force is the pressure difference that causes the flow to drive. The gravity is very small. It's not valid if you have a huge pipe, like a pipe with the diameter of like 10 meters, like this size of building, which is very, very exceptional. In that case, this is not zero. These are zero because the gravity is in the water, right? So in that case, it's going to be negative rho times G in that case. But for this problem, all of them are zero. Now let's talk about these terms. This term, I don't know it right now. This term also, I don't know it. But what about this term? Zero. In the z direction, there is no change in the pattern of u, right? This is zero. Now let's go to these terms. What about this term? Do I even have velocity v? You see, everywhere v is zero. So all these derivatives are zero. And these terms, these are all zero, because v is zero. See, v is zero. What about these terms? The w is zero everywhere, right? So this 0, 0, 0, and that means this also 0, 0, 0. Now, you see, most of the terms become 0 except some terms. So that's what I'm going to write here. But as this a little bit more whiteboard goes up. Turn it off. So the first equation simplifies to this. Partial u, partial x, you see, this one, times rho. Everything else is 0, except this term. So this is a continuity equation. The momentum, we get rho u, partial u x, plus equal 0, right? And is equal to alpha. So this is the pressure drop is constant, I call it alpha. And then plus this is 0, these two are also unknown, but this one is 0. So I say mu times partial 2 u partial 2 second derivative of u is 1. So that's the second equation. What about the third equation? The v momentum. We get everything on the left side, you see, is 0, is equal to, here, you get negative p y. This term is, I don't know, is not 0, but the rest of it is also 0. And what about the z momentum? Again, you get 0 from left side, and then this term is, I don't know, but the rest is 0. So equations, they will boil down to this set of equations. Now look what happens. The density times something is 0, and I know the density is not 0, so what can I say? From continuity, if I solve continuity, the derivative of u with respect to x is 0. Now use that, put it in the second equation. What can I say? You see, this is the derivative of u with respect to x. 0. What about this term?
0.
0. You see, this is what? This is nothing except
The second derivative.
the derivative of derivative u with respect to x. Right? So if this guy is 0, that means the second derivative also 0. And this guy will tell me this must be 0, right? So the pressure gradient in the y direction, 0. And this tells me the pressure gradient in the z direction must be 0. Right? Okay? More simplification. So this will reduce to the first equation, partial u partial x, 0. The second one, I get what? 0 is equal to alpha plus 0. The second derivative of u with respect to y. If this one is 0, and then partial p partial y 0. Third equation, and the fourth equation, partial p partial z is equal to 0. Now look at this equation. So what do I have here? Well, these are equations already solved. So this tells you that the pressure is constant in the y and also in the z direction. So that means if you come here, the pressure is constant in the y direction and also in the z direction. You don't make an assumption. This is what the equations, when you solve equations, it tells you, it forces you that the pressure in this direction and this direction is 0. But in this direction, the pressure is constant, the pressure drop, which is equal to alpha. So that's for pressure field. What about velocity? field. Velocity field, you already have velocity in u, the derivative is zero, but u is not zero, the derivative in x zero, right? Now for this, can I solve this equation? So if u in the x is zero, that means u is only a function of y. Do you agree? So that means this simply is what? This is, take everything to the right, you get the second derivative of u with respect to y is equal to what? Negative alpha over mu. Just rearrange that, keep the second derivative here, take alpha to the left side, you get negative alpha over mu, and then solve this equation. How do you solve this equation? This constant, right? This just constant value. How do you solve this equation? Yeah, absolutely, right? This is what we're going to have in the final exam. So if you don't know how to solve this equation, you really need to go back to the basic calculus and repeat it. Because in the final exam, I don't say, well, you know, this is what is in your book, and this is what we're going to ask you in the final exam. So our first integrative, the first integral, is going to give me u du dy is equal to negative alpha over mu times y plus c1. And then one more integral is going to give you u is equal to negative alpha over mu y squared over 2 plus c1 times y plus c2. So what is it? Look at it. U is a function of y. But what type of function of y? Is it linear function? Constant function of y? What is that? It's a parabolic, second order. Which, in fact, interestingly, it happens through observation. This is observation. This comes from lab. This comes from the maths. These are two different words. Right? But they match. Now, how can I get C1 and C2? How can I get these two guys? We had this in the first 2-3 chapters. Yeah, remember applying the boundary condition to say if this is, let's say the depth, this is from here to here, this height, call it h. So in fact, your from here, 0 to the top is h. From this 0 to bottom is negative h, because u 0 is just in the center. You see that? So I can say u at y is equal to positive h. What do I have? 0. It's a wall, right? Here there is a wall here. The velocity is 0. U at y is equal to negative h is what? 0. There is another one here. So let's substitute those values, see what we get for C1 and C2. So if I put u is equal to y, u at h is equal to 0. What do I get? 0 is equal to negative alpha over mu h squared over 2 plus C1h plus C2. So put positive h, we get negative alpha over mu, h squared over 2 plus C1h plus C2 is equal to 0. That's the first boundary condition. The velocity on the top at h positive is 0. Now put h negative. U at negative h must be 0. What do you get? 0 is equal to put negative h. Again, you get negative alpha over mu, h squared over 2, just like this above. But this one, we get negative C1 as part of h. It's a negative h plus C2. Now, these are what? I want to solve for C1 and C2. These are what? Two equations, two unknowns. And I'll have to solve the system of two equations, two unknowns to get C1 and C2. So let's do that. Let's subtract the above from the bottom. So you get negative alpha over mu h squared over 2 plus c1 h plus c2 minus the bottom, which is plus alpha mu squared over 2 plus c1 h minus c2 is equal to 0. Just subtract both of them, both sides of them. So 0 minus 0, this minus this. It should be equal to one equation. So this cancel out, C2, negative C2, these two cancel out, and then you get what? You get 2 C1H is equal to 0. Alright, let's use a different color, make sure they cancel out. So this cancel out, and these two cancel out, and then you get 3C1 times H is 0. That means C1 is what? 0. Okay, if you put C1 is 0, what do you get from C2? Either this equation or this equation. We're just doing Gaussian elimination. We're not doing anything. So in this equation, put C1 is equal to 0. What do you get? C2 is equal to alpha over mu h squared over 2. That's 3C2. So the end result is this, the same equation, but we already found value for C1 and C2. So I'm going to replace it. Plug in the equation, your end result is u of y is equal to negative alpha over mu y squared over 2 plus C1. C1 is what? 0, so I don't write it. Plus C2, which is plus alpha over mu h squared over 2. Now let's factor out alpha over mu 2. So you get alpha over 2 mu. Factor this coefficient, alpha over 2 mu. You get what? H squared minus y squared. Alright, so that's it. So u, the end result, I'll write the end result here. U of y is alpha over 2 mu h squared minus y squared. Look at it. What I did here, I solved Navier-Stokes equation. This called, you remember last class we said this equation with the viscous term, with the existence of these or viscous term, are called Navier-Stokes equation. And in general, you cannot solve it for arbitrary case of fluid flow. It's impossible to solve it analytically. You have to use computer. But look, for a special simple case like that, I was able to solve it. Navier-Stokes analytically and get analytical relation. Now in the verification, is this really valid? Look at the physics. Does it follow the physics? Does it match the physics? What do I get if I put y negative h? The lower wall. This is the lower wall. Lower wall. What do I get if I put negative h for y?
0.
The velocity is 0. Right? You agree? What do I get if I put positive h? 0. So both velocity and both walls, this is the upper wall. See, this is the upper wall. And this is the lower one. Right? In both walls, the velocity is 0. So can you tell me what's the maximum velocity?
H is 0. So I get for H being 0.
What should I plug in?
Y equals 0.
Y is equal to 0.
Y equals 0, right?
So what do I get if y is equal to 0?
Alpha over 2.
Yeah, you get u max. It happens when y is equal to 0. So you get alpha over 2 mu h squared. That's the velocity at the very center of this pipe, right here. Now we have one more example, I just want to show you before we leave. And I saw that next class, and then we do dimensional analysis. So next class, Friday, we'll start chapter dimensional analysis. So this is the problem we're going to solve in this class, is example 7.12. That's the problem. Example 17.12, and we are going to use, again, we are going to write these equations. That's what we are going to do in the final exam. I'm going to give you this equation, and then you have to show me which term is zero, which term is not zero, and then you simplify it, and then you solve it, and then you give me the final result. All right? So this is what we're going to do for this system. Now you see, this oil is kind of pouring over this edge, and it comes down with a constant velocity. So we're going to talk about this problem, and how we can start with Navier-Stokes and get a solution for that. Yes, yes. What